In the last video, we covered the concept of equivalence classes. Now in this video, I'm going to prove a special property concerning equivalence classes. Suppose we have a set, let's call it A, and let's say we have a relation R, which is just a subset of A cross A. And suppose we know that the relation R is an equivalence relation. Now what I want to prove in this video is that for the objects A, B, which are elements of the set A, what I want to prove is the statement that the equivalence class of A is equal to the equivalence class of B if and only if A is related to B by the relation R. So this is the statement that I want to prove in this video. Now in order to establish this if and only if relationship, what I have to do is to first we need to show that if we know that the statement A is related to B is true, we need to show that this immediately implies that the equivalence class of A is equal to the equivalence class of B. And then we need to show that if we know that the equivalence class of A is equal to the equivalence class of B, so let's say if we know this statement is true, then this immediately implies A is related to B. So in order to establish this statement, we need to conduct these two proofs separately. So we need to prove these two statements separately. Once we've proven these two separate statements, then we would have established this statement here, which is what we want to prove. Now in order to carry out our proof, we're going to first focus on this statement. So we're going to start off with the statement, if A is related to B by R, where R is an equivalence relation, then class A is equal to class B. Now in order to prove this statement, in order to prove that these two sets are equal, one way to do this is to show that class A is a subset of class B, and also class B is a subset of class A. So if we can show that these two statements are true, then we would have shown that this statement is true. So what we're going to do now is to show that if we know that A is related to B, then this immediately implies class A is a subset of class B, and class B is a subset of class A. So we're going to focus on establishing these two statements now. Now let's first start by proving the statement class A is a subset of class B. In order to prove the statement, we need to go back to the definition of what is a subset. Now if we want to show that this set is a subset of this set, what we need to show is that every element of class A is also an element of class B. So we start off with some arbitrary element x, which is an element of A, and then we should be able to show that x is also an element of B. And if we can show that, then that means every element of class A is also an element of class B, and that would mean class A is a subset of class B. So what we need to prove now is to show that x is also an element of class B. So we first start off with the statement. First we know that x is an element of class A, where x is an arbitrary element of this set. Now since x is an element of this set, recall that class A is actually an equivalence class. So by definition, so going back to the definition, this is the set of all objects in the set big A such that x is related to small a. So what this means is that if x is a member of this set of the equivalence class of A, then that means x must be related to A. So we know that this statement must be true. And also recall that we have also assumed that A is also related to B. So we also know that A is related to B. So right now we know that these two statements are true. We know that x is related to A and A is related to B. And don't forget, R is an equivalence relation. So R is actually transitive. So if x is related to A and A is related to B, then this would automatically imply x is related to B. And since x is related to B, by definition x must also be an element of the equivalence class of B. Because once again we go back to the definition. An object is only an element of this set if it is related to B. And since we have just shown that x is related to B by the transitive property of R, then that means x must also be an element of B. And so this shows that for any arbitrary element of class A, it must also be an element of class B. So this effectively shows that class A is actually a subset of class B. So this concludes the proof for this part. Moving on, now we want to show class B is a subset of class A. And the reasoning is going to be very similar. So we start off with an arbitrary element x of B, and now we want to show that x is also an element of class A. And since x is an element of class B, this implies x is related to B. And also don't forget, we've assumed A is related to B. So we know that A is related to B. And since A is related to B, since R is symmetric because we know that R is an equivalence relation, then that means B is also related to A. And then so we know that X is related to B is true, and B is related to A is also true. And using these two statements, now we can use the transitive property. Since X is related to B and B is related to A, that means X must be related to A. And since X is related to A by the same reasoning as before, now we can show that X is also an element of class A. And so for any arbitrary element of class B, it must also be an element of class A. And so this effectively proves class B is a subset of class A. And so this concludes the proof for this stage. So at this point we've basically completed the first stage of our proof. So we've just shown that B is a subset of A and A is a subset of B. And so we know that if we assume A is related to B, if we know that this statement is true, then these two statements are automatically true. And since A is a subset of B and B is a subset of A, that means A is equal to B. So we've established this statement. If A is related to B, then this implies class A is equal to class B. So the first step of our proof is complete. We have proved this statement. And now we shift our focus to the second statement. Now we want to show that if class A is equal to class B, then this would imply A is related to B. So now this is the statement that we want to prove. Now in order to establish the statement, we first make the observation that A is an element of class A. And we know this because, once again, we go back to the definition. Class A is the set of objects from the set big A such that X is related to small a. And since R is an equivalence relation, we know that R is reflexive. And so small a must be related to itself. And so since small a is related to itself, so small a must also be an element of class A. And so that's why we know that this statement is true. And then since for this statement, we're assuming that class A is equal to class B, since now we know that A is an element of class A, since A is equal to B, I can just substitute class A for class B because they're the same thing. So we also know that A is an element of class B. And then once again we go back to the definition. Since class B is defined to be the set of objects in big A that are related to B, if A is an element of class B, then that automatically implies A is related to B. Otherwise it would not be an element of this class. And so there you have it. This is the statement that we want. So now we've just shown that if we assume this statement to be true, then it automatically implies A is related to B. And so this concludes the proof of this statement. And so we've established this second statement as well. And so our proof is complete. We've just shown that these two statements are true, and that means class A is equal to class B if and only if A is related to B.